kind introduction. It is my great pleasure and a very big honor to be delivering this Dr. Bhave Memorial Lecture. The topic that we have chosen for today, well, I want to talk about JalTantra, the software that we have developed for water network design. But rather than going to technical details, I want to talk about why we did what we did. What are the issues faced? What has been the journey so far? Who all have been the co-passengers? And how does one go about doing this? And many of you and a lot of young people in the audience, what to look for, what to do. So of course, in some sense we can say the roots of JalTantra lie in the pioneering work of Dr. Bhave. Since, like I was just mentioned, that I was just being born when Prof. Bhave started his PhD on the issue of optimization of water network system. So his work still inspired, and throughout the development of JalTantra, you keep referring to these books. And if you see, so there is a design part and there is an analysis part. So there are two, and there are two different concepts. And so in some sense, you can say that I have been sort of, while everybody works on everything, specifically the design part, we have taken a little bit forward with JalTantra system, while Professor Rajesh Gupta worked with him on detailing the analysis and resulting in the wonderful textbook. So I am especially thankful to Professor Rajesh Gupta because just this year we got the news, and just now, this manual which had finalized last year and it's coming out, it's thanks to Professor Rajesh Gupta's effort that now it has been included in the. So while you know that JalTantra is already being used in large part of the country, it is for the brain engineer to decide on their own. Like in Maharashtra, it has been officially recognized. In some states, they say no, it's not in CPHO. So you can now with CPHO, even in the rest of India, without fear, will start using the JalTantra. So thank you, Professor Gupta, for that. So a work of this magnitude, of course, I am here, but I am just representing the team JalTantra. You see, there are a large number of people from different domains. It has been interdisciplinary work, and that was my theme of talk today. That any work that touches the society, that you want to have an impact, it has to be an interdisciplinary. While of course the professors and guides are in the middle so I will talk about the last column specifically. Rest of everybody is from IIT Bombay. So several professors from computer science, urban science department, and IWWA Industrial Engineering Operations Research department. So, and then there are several students, BTech, MTech, PhD students. The project staff, TDSP, our Technology and Development Solutions Cell, our project coordinators. The last column I have put as an honorary member of Team JalTantra because each of them had a very special role to play, and without their support we may not have been where we are. So of course, Sri Santosh Gavankar, who at the time was in Nagpur, and of course, this western part, the eastern part of Maharashtra, always been pioneer in water network thing. So Sri Gavankar, who attended earlier, we were struggling, we have designed some system, we are presenting in various fora. And so the Chief Minister had invited a special technology for development kind of workshop where I happened to meet Sri Gavankar. And I spoke for 2 minutes about JalTantra. He got excited. He came back to Nagpur and he started using it, even though it was not official. Nobody wanted to touch it, saying no, it doesn't. And then he gave us feedback, and through the show that was included. So Rajesh Gupta, of course, you all know, and also like I said, he has gotten us in CPHO. Sri Pradeep Gokhale is also again now retired from MJP, but he took deep interest in our work, gave us feedback, helped us promote. So like with JalTantra or the other work from our group, like Professor Pradeep Kalvar's multi-SAP technology and others, Sri Gokhale. So in some sense, I see them as part of the team without whose contributions JalTantra not. One is the development of technology, otherwise it's adoption and distribution, where the last they hopefully have been the pillars. So other than that, there have been large number of students and interns and what we call technology and development project support. summer student, interns who went. And the idea before we, to design this has been a long journey. And I will talk, but the point here is that we visited lot of drinking water schemes on ourselves. When I say all these projects mean the student goes out to a field, stays in a village, studies a drinking water scheme. And I have personally visited over 100 drinking water schemes myself in more than 100 villages over the years. And like so, sometimes when you wonder whether you, so this, how did he start? In 2004 December, I joined the IIT Bombay as a computer science professor. Professor Milind Soni, who was also with computer science but also with Tara Center for Technology for rural area. He started working in the, he and many of us had this urge, okay, we are developing technology, but we want to work directly for social development. Technology will develop will also have a long-term impact, but we also want to solve some immediate problem, engage with society. So the first thing we did, and I went to this Guruvayawadi checked project was sort of the starting of our drinking water group at IIT Bombay. We engaged with the government of Jal Swaraj and a number of multi-village and single village schemes we studied. Basically going to tribal villages within 2-3 hours of Mumbai, engaging with people there, understanding why did the scheme fail. So this is sort of the till 2011 I was just going with them. I said Professor Soni was leading all this effort. Till 2011 I had not much role other than just getting exposed and learning about it. I was exploring many things, drinking water being one of them. Right? But so what really happened if you see this, because I was in computer science and Milind and Guru, now Professor Pradeep Kalwar from CUG there. Over the years, we developed this approach when we talk about this drinking water work there and pipe water network that I will talk about rest of it. So this is the idea that there is a technical component, but there is also a social. By social, or you mean individual component, going out, engaging with government, engaging with villagers, and they are in the opposite direction. So if you see, so while most of the time the university research stays in that second level, at tools level. Modeling, simulation, optimization, GIS, decision support, all of them. To be successful, to really solve the right problem and solve the problem the right way, we need to go down. In case of rural problem, you have to go to village. In case of urban problem, whether it be Islam or it be a housing society, you have to go there, engage with people, understand, and then systematize it. So one thing that academics do is take an informal description, have a conversation, and then try to formalize it. So that's what we mean by systems level. Understand what are the components, because each person is focused on their system here and now. Academics can piece together the big picture. So doing system level analysis, developing best practices, and various stakeholders. So this is the work of what our drinking water group at IIT, or water group, not just drinking water. And then, so that's the first level analysis of what is happening on the ground. Then doing what we are good at, modeling, simulation, optimization, data, and now of course AI, ML, all of that has come into the picture now. And finally, this is the level where most of our academic work is taught. But if you want to have an impact, then taking it, running after government officials, planning bodies, and giving them input and trying to get them to incorporate it. So like you see, so it has been a long journey, and finally this year it is making to CPHO manual. Our that JalTantra itself started 10 years back, and our water work started 50. So it has been a long journey, but it has been satisfying. And so what did we learn? See, the work started this specific work when the NGO JalTantra in culture. They just on the net saw IIT Bombay has a drinking water group. They contacted us saying every summer we have drinking water crisis. Our pipe water scheme failed. And they said, we don't know what to do. We can just go and hear out the collector. Can IIT help us? So we said, okay. We were unsure. We went and visited, like I said, we visited the villages, studied, tried to get. Essentially said, why did the drinking water scheme fail? And what we understood was, initially each problem, there was some small technical problem. And therefore the scheme starts failing partially, little bit. Maybe the tail end of the village will not get the water while the scheme is mostly working. Or some time of the day you will not get the water. then some villagers pull out. So the talented people will stop paying for this service. Then maybe the maintenance get. Other thing happens when some villagers pull out. Others who are getting the service also stop paying. Because they don't know who is actually going in. They say, oh, that guy is not paying, why should I pay? Without worrying about who is getting what quality of service. So this creates a vicious cycle. So then if the financial problem develops, then you will have even less money for maintenance. So then some capacitor will burn or some motor will burn. And so the technical problem will become worse. And so you get stuck in this vicious cycle. This is after analyzing few stages, this is what we figured out. And we said, fine, there are many elements of this, technical, financial, social. But let's start with the technical problem. And because we could see that there are design problems when we could simulate on Upanet and other things. So we started engaging with the rural water. We tried to engage with rural water supply engineering. Initially there was a lot of resistance. So government engineers say, oh, you guys professors don't know anything about the problems we face, the constraint. We have a very strict norms for designing. The CPHO manual, first time I heard, we have to follow word by word. If because of that, following CPHO manual, there is a problem in the village, I can't do anything. I cannot deviate from CPHO. So he said, fine, but so we said, don't worry, we want to help you. We are not here to talk about some other best system. That is the crux of that we patiently work with God. We assure them that we will do whatever you need. Our aim is to help you, not to criticize you, to understand your problems and figure out wherever is there some part of your problem that we can solve. Because you understand you are also want to work for society. There are various constraints that you work on. I think that part was very important, that whoever you engage with, understanding their constraint and concerns rather than thinking that here we have this great idea and here is this latest technology. And so eventually the key point that came was that there is strict government norms for per capita cost, and if the village topology and other things do not allow a good system, then that's why some of the schemes fail. We said fine, therefore cost optimization became important. And if we can if we can design a system at lowest possible cost, then we get the best possible network. That was one insight from our view. The other aspect was, of course, that we as IIT, technology is our strength. So that gives us, even for the financial, social issue that we uncover. Because we have a technical tool, people will hear us on those. Otherwise, they won't hear who are we. Why is some computer science professor coming and talking about the financial or social problem or the lack of maintenance fund? So that's how we got started on the work. And then what we over time discovered that there is a big knowledge deficit, unfortunately, in the technical. The way various things are structured. I won't go into why the root, but this is what I was offering. So the basic of hydraulics and optimization, the government engineers, many of them were not regular. There were some truly excellent engineers, many of them I named, with whose support we could do all this. But there are many others who are burdened with or new people who have not been given proper training. So we realized that those have to be brought in, and then modern tools like GIS simulation were not being used. And then protocols rigid and frozen in time, like CPHO manual now being updated after 25-30. Of course, there are various constraints. This is an all India thing covering many things. Finally, it takes a long time. So, and in the process, we also said, look, this knowledge and tool is also, in some sense, when we talk about development, sometimes we think of development as a political problem. Or we say, oh, because of the caste, because of this or that, or whatever it is, there are 100 factors we can count which is not technology. But what we must realize is that technology also, in a way, is a politics. Politics is about trying to influence policy. Politics come from polity. Right? So politics is about different group trying to influence policy. So same way, when you give a tool that says here is the best location for the tank, drinking water tank in this village, then you are trying to, in a way, you are registering if there is a caste-based discrimination or issue in a village where certain caste will decide that the dominant one will decide drinking water tank should be in this area, not that. Then you are giving a technical response to that. That's it. And like I said, there were social issues, some of these will uncovered. And technology becomes a tool, but one has to be conscious of it. Otherwise, if you just engage with the dominant people, when you go to a sarpanch whose house you will get to stay in the night, usually it's sarpanch who will offer you the lunch or dinner. Or so then you only engage with dominant people, and then their view, their biases will affect you. Of course, we try to make sure that we go to different part of the village, engage with different people, both in. So we read the census data about the village and various data sources. Go to different part, speak to men, women, young, old, in all our work, I'm saying not just water work. And so similarly, when you tell the problem, when the government engineer have told them this is not possible, people are just okay, engineer ne bola, hum kya karenge? But now, so when we say a solution, they say, oh, but IIT says it's possible, and I will talk about it, that played a role. So that becomes a, then they can go to their MLA, their punch, their MP and demand a solution. Earlier also they were demanding, but they didn't know whether it was possible or not. So in that sense, what I mean is contributing to political process, because change finally comes from certain political process. And so our task, the point here is that we as academics, our task does not end with scheme design. Who will listen to it is important. While I talk about some success, we also have failed it. We have tried, finally we have our limit, system has its own limit. I'm happy that some of the successes we had. I'm sad about some of the failures we could not influence it. We have the solution, it could not be implemented for various reasons. So anyway, so this was the main point for A, that the government norms are important, so the cost optimization is important. Then there are various things, source selection, tank district, where the tank should be located, who should get water from which tank, why location. At the time they were being done based on either people's own experience, which was good for experienced people, but for newbies it was ad hoc and random. And then the existing software were either very expensive or very old, 20-year-old software, so not suited for the modern day technology. So for example, something runs only with DOS and not with Windows or the latest version of Windows. They had network size limitations, they will not be best for. Sometimes they will not work. You make a small change, and the same network will not be solved, and the source code is not there, you cannot include them with the. So those are our goals for this. So this was then we came up with the problem statement that we come up with a free and optimal design system that will optimize the overall steam cost. And first part of it was because rural network, mainly the pipes constitute more than 50% of the cost. So first version of the problem, we only focus on pipe diameter, which is what was typically optimized by engineers. The other thing like ESR, location, pump, all were being done in ad hoc. So but we said that let's make it part of the optimization process. Let's do a simultaneous optimization. So I think JalTantra is the only system to my knowledge which does all these possible optimization. And at the same time being fast, free, optimal, and a large network. But while being technology advanced, it should be very easy to use. Otherwise, new engine people don't like to change their way. Every new tool user, it is a great tool, they say, oh, I have to learn something, it will disturb my process. So there is a lot of resistance we also face. So we were very keen and clear that people have to find it very easy to use. And whatever their own reality is, we have to respect it. And help government improve the process. So that was, finally I think we success. They are not trying to criticize other people that what you are doing wrong. But saying whatever you are doing, the problems you are facing, there is how we can help. That has been our focus. So of course many people here would know it by heart, but for benefit of some people. So this is a typical multi-village water scheme. There is a main tank, MBR, mass reservoir. Then there are the ESR, elevated storage reservoir. So from MBR, the primary network goes to from MBR you fill the ESR. With each ESR, then we will fill a subset of village. This is a very, and this part is called a secondary network. So this is the base. So what is the water network design problem? Like I said, first is the pipe diameter. What pipe do you use? Usually pipes come in discrete sizes. So there is a set of 4 or 6 or 10 types of pipe. You say for each link in the network, I have to use one of the pipe. And usually those are identified by their diameter. Pump size, how big should the pump be? Because pumping, not the pump, but there is energy cost associated with the pump. So 5 or 10 ESR. So where should you go? And which village, allocation of villages to ESR. Some villages may only be close to 1 ESR. Some other village may be close to 3 different ESR. Which one should serve what? And that affects the cost. So this is the very broad problem statement and component. But I will first look at the most simplest possible problem. So now what was the existing state of the art? Of course, till then also people were designing it either using Excel and InterNet or using certain software which were made various assumptions. Some of them did not have this only 6 type of pipe. They will assume that I have a continuous diameter. Just mathematically find the base diameter. Say 3.72 meter. Why or 3.7 whatever inches. Why it may just come in 3 and size 3 and size 4. Or they will assume, so suppose you have a 1 kilometer long line. Then they will say, okay, only one type of pipe can be put. While an ideal solution may require 2 pipe, okay, only half the section or 60% of the length you use one diameter, 40%. Then there are other solutions which was either they were using a specific solution. There were other people who were not making these assumptions, but their solutions were not optimal. So they were using the genetic algorithm, mental restriction. So what was our approach? We said, look, this modern optimization. So it's also, see, earlier people did with the technology that was available there. By our time, newest technology, more faster, efficient, what we call compiler and solvers were available. So this modern optimization solver had become pretty fast. Now, by optimization, we mean you just give a specific, and you say, this is what I want to do. You have to be very careful with what you say. It's like this, say you know a computer program, you know a Fortran program or Java program or C++ program, right, or a Python program. That is compiled by a compiler into machine language. Instruction, the bits and bytes, the zeros and ones, the binary language. Early on, 30 years back, people will be very careful in writing their Fortran program. Say, oh, I should put this instruction after this. Then I will get efficient code. Later on, compiler became so far that you say, no, you just think about the right way to solve the problem. Machine code will be generated by compiler. So same thing was happening here. So for example, like what he said, focus on algorithmic complexity. Do you make one pass over the network or do you make n pass over the network? That is what will make the difference, not whether the generated code will be 20% fast or so. Just the way databases, those of you who use it. Now we think in terms of schema, which table is related to which table. We don't think how will it be stored on file system. So this is called process of abstracting out. That progress in computer science is about hiding the low-level details, saying give me a good high-level specification, and software will solve it. So same thing was happening here. So this is why we decided if we get a good specification, the modern solvers will solve it. And if you are not clear, I will give you an example of what I mean. So first the problem statement. So for example, here is the example network. This is the source. These are 3 different nodes. So there are some elevation and some demand. And the 3 different types of pipes are supposed available. Then an optimal solution is shown there, where you see 2 of the link, just 2 different pipe sizes, pipe diameter. And then there is some cost. So this is the problem statement. Given a network of this type and the cost for the commercial pipe, come up with that solution on top right. That is the basic problem, first problem we will solve, which is what was being done by most people at the time using Excel, InterNet or branch and other existing things. Now suppose we formulate it and suppose for the time being you only say let me have a single diameter for the whole link. So this is what is called a linear programming formulation. This is a mathematical statement of what you want and what are the constraints. So for the general audience, we will not go in the detail. This is what I mean. If you write a program like this, literally what is given here, of course, it will make some work to translate right into a programming language. Then the solver will tell you the answer. So we are spending our energy how to write this thing, this mathematical concept properly in the program. We are not trying to develop algorithm to solve it. That is the beauty of the modern solver. So essentially, say, take the length of the pipe, look up the cost, xi3 is a binary, is this pipe, is this the chosen type for this or not? There is a node constraint. You start from the source of the network. As water come along the pipes, there is a pressure loss. By the time it hits each node, it must reach the minimum pressure requirement. You know, like rural area 3 meter or a 5 meter, urban area 7 or up to 20 meter in depending on the area. So the source network, you start with some very high pressure, there is a friction loss along the way, but you must have at least this much pressure at each node. And of course, you must meet the demand for that. So this is on the right, there is a formula for the loss, the Heisenberg equation, the loss of the flow, and this stage only one of the pipe type being chosen. Next. So the problem is, this is what is called NP hard problem in computer science. Essentially, people say it is close to impossible to solve the general problem efficiently. You have to spend a lot of time and days to solve that is the key idea for some instance of the problem. Meaning this problem, of course, some examples of the problem can be solved very fast. There will be other networks where you will take a lot of time. Next. Now the mathematical results say any best network will have only 2 types of pipe. You may have 100 types of pipe available to you, but the best solution will only have 2 types of pipe. So we say, okay, let's use that idea. Right? So here is the same problem. Now we are saying use only 2 types of pipe instead of 1. So some minor changes, but now what we call problem has become non-linear program. Essentially, the problem, so let's ignore the why, so this is mathematically become even harder. That's the main point. It's a very similar formulation to those who are mathematically inclined. I can share this slide later on. Basically, now in each link, say here to the nearest water tank, you can have at most 2 types of pipe. So X1 and X2, each represent which pipe diameter has been selected. Rest is the same thing. There is a pressure loss along the path, and the 2 together lengths should make the length of the pipe. That's the constraint. Next. So then we do something. We say, fine, this is a mathematically hard problem. We do some mathematical transformation. But that next. So what we say, okay, fine. You should think again. When faced with a very hard problem, either you can move hard, or you should say, can I solve a slightly different problem? Can I solve? My current approach, the problem is becoming hard. I am going to buy more memory, more CPU. I am going to throw a lot more energy at the problem. Or I have to step back and think. Can I think about the problem in a different way? Next. And this is what we get. In a way, it's a very simple insight, but it led to beautiful result. You say, why worry about 2 links? We will say, you can use all possible 100 diameter. We are not going to say use only 2 diameter. Now, mathematically we know that the best network will have only 2 diameters. What it means is the other 98 will have 0 length. But we will say for all 100, please tell us the length. So it actually simplifies the problem. You think it's complicated, but with some mathematical insight, we realize that this simplifies the problem. Because I've gotten rid of selecting this pipe to be used or that pipe to be used. I'm just saying, give me the length for each pipe. So it's like it's very simple, but in some sense simple, but some sense deep. Some deep insight also, which helps actually simplify it. If you look at this, the formula, forget if you know that. Just looking at it, you can see it looks simpler than whatever we had the previous 2 slides we had. So in some sense, it simplifies it tremendously. This insight. Okay, let me solve a more general problem than this very specific problem of 1 type of pipe or 2 type of pipe. This was, I would say, a killer step, a killer insight that most people are not in. It was very simple. At least once if we have gotten the insight, it looks very simple. It requires us to keep thinking about it, what is making it hard, what is this, that. And of course, requires some knowledge of mathematics to figure out that this will work. But this was, I remember how I and Nikhil Huda, we were sitting together on a piece of paper. This is only the napkin thing. We were also just working on some rough piece of paper. Oh, where are we facing problem? And we were discussing in our guest house guy, sitting there. And suddenly this thing came. Let's try this. And it worked. Next. So then the rest of it is now I will skip, but we will show essentially why the number of variables in the program went down dramatically with this insight. And they are solving time. Before, a 10 node network was taking over 100 seconds. Now we could solve 1000 node network in 1.5 seconds. Which means we could solve any net. 1000 node is sort of the biggest network you will encounter. And that was being solved in 1.5 seconds. Earlier system could not solve 100 node. This was a tremendous improvement, 100x improvement, aided by some mathematics, but also by, of course, by just banging your head and keep thinking about it, The final insight was simple. Anyone here, any computer science student, any civil engineer, any mathematician, I'm saying you don't need to have a very high mathematical knowledge. You need persistence. You need to have basic knowledge. The minimum knowledge is needed, not maximum knowledge. But after that, you have to keep thinking about it, and then in your head somewhere the solution pops up. Because remember, I am not a water network person. I am a computer scientist. Of course, we interacted, we got input from the engineers and others we have mentioned, we studied the books, 2 books written by Professor Bhave, and whenever we needed help, you would go back, clear up our concept. But finally, you must realize we had a minimal knowledge of water network. Even today, I had to call a few people and Baba, I am going to give this lecture, I shouldn't make a fool of myself. There is some tough question about a water network. But finally, I am a computer scientist, not a water network. But we could do this because we said this is an important problem. We want to help contribute to this solution in whatever way we can. And then we managed to reach somewhere. So with that, I will actually showing some example, same thing that these are some of the real life network, some of the artificial network we generated for testing purposes. So we could generate a 1000 node network, and we show branch was the existing tool being used. So it could not solve even a 100 node network. I don't blame it. Branch was designed 30 years back for a different time, and then things were not. So this was a popular model, 1.5 model. I said some people were using, and our model, as you can see, it can solve even 1000 node network. It takes the least time and it gives the best cost. So it's not a trade-off. Okay, if you take less time, your cost will go. So you can get the best possible cost at the lowest possible cost. So that was very satisfying. So this is again something interesting. This is a side insight for. See, it's also we are using a number of solvers. The initial solver we used were also actually inefficient. The one we use now is more efficient. Maybe if the one we are using now, if we started with that, with a powerful solver, then we would not have made so much mathematical improvement. Like they say, sometimes the necessity is the mother of invention. Because we started with somewhat inefficient solver, we had to keep thinking mathematically. That worked in our favor. Then later on, when we got mathematical insight and we can use solver, now we are confident we can solve very large network. We can meet the need of the future. Who knows, if we not started with that, then we would have very powerful solver, it would have solved the problem, then 10 years later it may have failed. So in a way, sometimes don't take the easy path. Don't, like I say, like a program is running fine, or don't say let me buy more memory and more CPU and solve the problem. First try to figure out why is it taking so much memory, so much CPU. Try to reduce the load. Then when later on at some point, of course you will have to buy more memory and more CPU. But not at the very first time. Like I am an IT advisor to many companies. This is my standard response. They say, sir, we need to purchase more hardware. Because as an advisor, they need my approval at times. And I say, no. You have to tell me why is your current system so slow. Without that analysis, you throw more memory, after a year it will again become slow. Suppose there is a memory leak in the program. It will consume all the memory you throw at it. So at least put some effort. We may not find all the reasons. Find some reasons. Improve your system a bit before looking for resources. In that sense, resources help us make done. It's not just all aspect of life. Like sometimes I worry. I grew up in a very simple family. In the sense compared to what we have today. And those struggles, sometimes we worry our children have not seen that much struggle. I'm sure most of us have seen. And we learn to live with a life with whatever we get and adapt to the circumstances that some of our children may not. Because they have been just used, they have not seen so much water, they end up getting most of the things that they want. And that may be bad for their future. So in some sense, same lesson applied here also, that try to make a program very efficient, be very sure of what, at least try. At some point you have to give up, at some point the students have to graduate, professors have to get promotions, engineers have to move on in life. So, next. So anyway, so that's will bring me forward. This was the very first version we developed, this was the interface, basically a desktop version. And remember, all this would not have been. Main issue was, like I told you, government engineers say, oh, this is not a approved software. I don't want to use something untested, unknown. Tomorrow, who will be blamed if your software passes an error? If it's an approved software, even if it gives the error, the engineer is not to be blamed. But otherwise, the engineer is to be blamed. Why did you use a non-approved software? But so there are some brave folks at Thane MGP office, and who started using it. Sri Mahesh Patil at Thane MGP office, who helped us, who said, no, this looks like a good idea, I want to work with IIT, I want to help them. Then I talked about Mr. Gavankar, so who from Nagpur he came, then I invited him again, he again came to IIT just to discuss with us after using it. It's constant, so I think Sri Mahesh Patil and Sri Gavankar, who were the working engineers, without huge support, active use, active promotion within their department, telling their other engineers in their group, please use it, and don't worry, we will see if the problem comes. And then of course Sri Gokhale, I said, who was a mentor for us. So system kept improving with their feedback. Then I will skip this part. So this is for the branch network. So this is why till now we were doing this pipe water thing. Now in the Mokhada, the Spashtakari Sammelan approached us, said, okay, there's so much, this is a hilly area, Palghar, Mokhada region. And there's a drinking water crisis. While all the Bombay water is coming from there, this big reservoir, Vetanna, no. So it was a shame that all of Bombay is getting water from there, the tribal hamlets there are not. And government engineers said, hilly terrain it's not possible to design in the cost now because the terrain is so hilly. So that's where we decided to explore alternative design. So I will now skip this part. Essentially now the idea is, because now I think we are out of time, where should we put the storage reservoir? There were two extremes. One is just have one reservoir for the entire network, other is every village put a reservoir. And we were saying in between there will be a place where which is the optimal solution. That is because next. Anyway, we will ignore all of this now. Essentially, I will just say that with the existing tool, I mean, I am not blaming government engineers for saying it's not possible, because exponentially very large number of, like millions of choices were there, and nobody can do it manually. So they were quite justified in saying, based on their experience, such a thing cannot be explained. Unless we make this problem mathematically manageable, this would not be possible. So none of the existing tools could solve. So even the software tools, not just engineers. So this where to place ESR, we brought in our optimization formulation. Next. Main point is I will skip the detail. Main idea is if you increase the number of tanks, your tank cost goes up, but your pipe cost goes down. And so there is a tension. When one cost is going up, other cost is going down as you move from one to a tank in all. So clearly there is a point in the middle, which is the right point, where these two costs balance out, that is the optimal point. So I will skip all mathematical details, but these points are explained in slide next that I just explain why, and then what mathematical text we had to play. Of course, we include this problem again, became very hard to get a PhD, which is good. Otherwise, how can you get a PhD without solving a hard problem? So the student, and of course with guidance from someone like us, we solved, and then we showed. So this is what we saw. Either you have one tank, you have some cost, you put a tank in every village, there is some other cost, and our system now shows you the optimal cost with only some of the tanks, and then each tank serving multiple villages. Anyway, so now these are all technical details. Someday we showed how again this program became very hard and we had to work next year or two. We had to keep again optimizing it. And the pipe water problem earlier I said was very simple. Once we made it simple, 1.5 seconds. But now it again went back to non-solvable category. So we keep analyzing it mathematically, keep making improvement while meeting all the constraints. That's the important part. So go ahead. Anyway, go ahead. These are all mathematical details of the things we tried. We just keep going forward. Next. Okay, just stop. Important thing is pursuit of simplicity and elegance. It was not that here is a great complex mathematics and see to impress others. So it's such a. He said, how do we come up with a simple specification? Is everything we have put in our formula necessary? Can we remove some of the things? It is that mindset. We are trying to make model as simple and general as we are questioning every concept. So engineers say, oh, this is needed, that is needed. But we are saying, okay, do you really need it? And one example I will say. One of the constraints was that in ESR you only put on a demand node. Suppose there are two villages 5 kilometers apart. Then your tank will be in either village 1 or village 2 or both. Engineers would say, we will not put a tank halfway between or somewhere along the road. Usually they were putting, which made sense in general, कि भाई demand जो है वहीं पर tank होना चाहिए, otherwise water has to travel extra. But because there are two villages and you may want to put one, we say okay. Is it okay if you put a tank in between the road? They were amused. They said, "ये तो wastage होगा, आपका तो optimal solution नहीं आएगा." डाल दो, but they thought of this. Okay, CPHO manual does not prohibit it. It's allowed. They said fine. So we included, and actually it led to simplification because we had to remove some constraint where to put the tank. So mathematically, otherwise we are saying tank has to be here or there. Now we don't have to say anything. Tank can be anywhere in the network. Now most of the tank will only be in the village actually. But or even if it's little bit away from the village, engineer can change our solution and say, okay, let me move it a bit later on. So we could improve that. Our solution time became very fast. And finally, you can see we could get a 200 node network in 70 seconds. So our first cut when we all this, the time taken was more than 24 hours. And eventually, over the 1 year of work, therefore, finally it would go to 70 seconds so that Nikhil could get into PhD. He also won the excellent PhD thesis research award of IIT Bombay and our computer science department for this work. But of course, our biggest reward and award is that it is being used by people more than anything else. In between, like I said, it's a political process. We Kodala village, we organize a water conference where local people and MP, MLA were present. We gave them the design. By tell your engineer that IIT says it's possible. Secretary Tribal Development and all also came. So some of these things we did. Then we publicized this version. After that, further things happened. I will skip that. Like we went to Rajasthan where the land is flat, not gravity. So that led to the issue of pump, which I had not touched. So that next, the pump was brought into the picture in our formulation. So we believe now we cover all terrain in India. The current version of JalTantra, whatever your need, we have a solution next for this rural water network. Keep going next. Anyway, just skip. This is something else to try. Alternative approach that did not work out, but this is just saying you keep thinking, try different things. Next, JalTantra. Okay, so this is the JalTantra 2.2. Now we will have a further 2.8 or something. But basic architecture detail, it uses certain libraries, certain solver, what are the web technology, all of those details. So this is the, then again some people said we have to do this, it would be nice if you can integrate GIS system. So this is what the current interface is. So this is really the story of JalTantra. As far as you go, I will skip the rest of the story of Fatafat Jatari. Just Jatari. So now there is of course natural next stop was the urban loop network. So 2017-18 this was mature being used. And now people were saying, oh, but I don't want to use one tool. Some people will say, that both rural, urban, I have to use one tool for rural, one tool for urban. Urban networks are hard because they have cycles and multiple paths. So there are various reasons why urban networks are much harder. We have been working on it. We have a good problem to have. It leads to new PhD, new student thesis. I will skip the mathematical details of what we are doing. We have a working version for loop network. That much I can tell you. It probably does better than most things, but it's not publicly released. Various reasons. But anyone who is interested, please contact us. It's still being developed, and it is at a stage where it can be used by others. But because urban networks are much harder, it takes a lot more resources. So we can't have 100 people trying. Also, there is we have to host it and provide resources, and we are paying Google Maps. So JalTantra is free. Code is open source. It's free in that sense. Cost-wise, it's free. But because government is supporting, or we have some grants to pay for all the Google Map lookup and all, but someday that cost has to be borne by Google. आगे बढ़ते रहिए. पूरा आगे बढ़ते. Just आगे बढ़ते रहिए. So I will skip all the mathematical details of what we are trying to do, because see, loop network, it is known theoretically also nobody can guarantee you optimal solution. So we can just say this solution is better than any other, which is what we believe we have right now. But it is not guaranteed. Tomorrow somebody else can do better than us, because mathematically you cannot guarantee that in finite time. So these are just the different things we tried and some combination of them that we believe is the best solution. And then there are a lot of different things we can bring in as practitioners, inside the tool, but multi-outlet tank, like Dr. Pradeep Kalwar is working on multi-outlet tanks and SAP and manifolds. How do we model them? With Pradeep, we explored we are modeling them separately, not inside system. The demand estimation from GIS, the issue of maintenance, DNZ and other inferring network. So there are a lot of things people looking for project and computer science engineering students. Here are a lot of ideas that you can do. Of course, your ground. Then the issue of groundwater versus surface water, bulk water, grade and everything. So it has some real world impact. And all of you know, I don't have to talk about it. It's heavy use. This booklet we wrote improving the performance, and it's being used in a lot of engineering colleges in Maharashtra. The one next. So Mitra, of course, now Maharashtra was the first state to adopt it as an official software before the CPHO manual. So next, so this just says even during COVID time we were conducting trainings for engineers, and there was a demand and people were excited about it. So important thing is we were getting real world feedback with the engineers. It was not just in our lab, in our computer, we have developed a solution here, please use it. It was a two-way interaction constantly, keeping stakeholder need in mind, and I think that is why we have been able to make something that people can use next. So this is what we say trying for interdisciplinarity. See, IWWA Department Computer Science, there is this and that. Then there is what TDSC, I said the consultancy cell that we have. So you need some outreach component. The professors have academic duty, you also need staff, engineer, project who coordinate this interaction between the three. All said and done, you can imagine it's very hard to interact with the government. Or sometimes very frustrating. Sometimes they are failure. So you need a dedicated cell center, dedicated people to manage that interaction. And then of course, as I component the development research, various venues. We have specialized courses that encourage the student to go out. The department like Sitara, but then there is a government, there are regional engineering colleges, there are other stakeholders, the NGP, the water supply department. So when they all work together, then something nice happens. That is the idea. I would like to leave it at that. Thank you. Thanks a lot. I'll be very happy to take any questions.
If the audience has some questions,
you can just one line. You can introduce yourself and ask if you have any questions. Now or later, but don't hesitate. Ask anything. It has been. I have presented a success. There have been ups and downs, and then it hasn't been easy. The student has worried sometimes, oh, will I ever get my PhD or not? All of those frustrations, sometimes there's excitement, sometimes so that engineer is never going to give us the file, we are wasting our time. All of that has happened, but we stayed at it.
retired professor from ENA. First, at the outset, I must congratulate the entire team who have developed this technology, JalTantra. Many congratulations to you. I have few